and get this started. So thanks everybody for showing up to the Tech Talk today. We were very lucky to have Stefan Lee with us. He joined OSU in 2019 as an assistant professor, and he's coming to us he got his PhD at Indiana University, and then spent a couple of years at Georgia Tech as a research scientist. And I kind of view him as a jack of all trades when it comes to AI. You can pretty much ask him about any area, and he'll have something interesting to say. And in particular, today, he's going to show some work on combining vision and natural language, which is something that's really just beginning to be done with any real capabilities in AI, and it's at the forefront. Traditionally people have focused on one or the other, and he's one of the growing number of researchers who are combining them. So without further ado, I'll let Stefan get started. You can ask questions in chat. Do you mind if people interrupt you during the talk, Stefan?
No, I don't mind at all. If you see something in chat, you're welcome to pass it along.
Right. I'll monitor chat, and we'll also leave time at the end for any questions as well. So take it away.
Yeah, thanks. So like Alan said, this is going to be a talk about my research area, and you may or may not have had exposure to it, but it's also going to be a story about pre-training and transfer learning and multitask learning and the power that you can get out of those sort of techniques. Again, in this domain that I'm interested in, but that's going to be the overarching narrative if you want to go and transfer this to someplace else. So just to get us started, I am interested in AI agents that can demonstrate their understanding of the visual world by responding to or generating natural language, right? So this is the broadest definition for what an area I'll refer to as vision and language research, which, as you imagine, combines techniques and problems from computer vision with techniques and problems from natural language processing. So this little thin slice here is where I do a lot of my work. And problems in this space have a sort of, a plethora of forms. You could imagine getting an image like this young woman making a sort of comedy mugshot here and asking a computer, what is her mustache made of? And a really intelligent visiolinguistic agent might be able to say that the mustache is made of bananas. Or likewise, if you are visually impaired and somebody posts a family picture on Facebook, you might want Facebook to tell you what's in the picture automatically, right? So you might want to have an AI that says, oh, it's a man on skis teaching a young child how to ski. And you can imagine taking this even one step further and being, a little agent in your house. You buy some robot to take care of your house, and you give it an instruction. You say, go left around the table along the back wall and turn right at the fireplace, blah, 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 end up next to the right bedside table. And you'd want the agent to be able to look around the environment, listen to what you say, and actually sort of go where you want. Maybe it's carrying something to the nightstand for you, especially in new environments that aren't just necessarily your home. And underpinning all of these tasks is this need for what I'll refer to as visual grounding. The ability to link things that we see with words that are used to describe them, right? In order to answer what her mustache is made of, you have to understand her refers to a woman, and visually that's the woman. The mustache is something that grows on the lip, and this mustache is a set of bananas, right? You have to transfer from pixels to these categories, which if you contrast that with something like image classification is a much broader vernacular, right? There's a lot more words in the language than there are people willing to label images for ImageNet. And same story here. When I'm generating language, I still have to identify the child. I have to identify the man. I need to know what skis are and what training straps are. And I have to be able to identify this activity, right? This man is teaching a child how to ski. And similar story for navigating. I have to be able to localize the objects that are referred to and know how to move about the space relative to these commands, right? What does it mean to go along the back wall? Or what does it mean to turn right? So they all have these very they always have this common need for visual grounding. And in the space of these sort of benchmarks and applications that people study in visual grounding and in vision and language research, you can imagine tasks like question answering, and there's some data set for that. And you can imagine generating descriptions or captioning images, and there's some data set for that, and same for navigation. And in fact, if you sort of take a step back as a bit of an insider and say, okay, what problems are people looking at in this space and what data sets are they using to evaluate them, you start seeing this landscape that's just chock full of data sets, right? So if I just want to talk about visual question answering type tasks where I have an image and a question, all of these data sets plus some more I'm going to get in trouble for leaving out address that problem. And if I care about generating descriptions of images, well, all these data sets address that problem. And if I care about navigation, maybe all these data sets, and so on and so forth, with a bunch of these random sort of data sets targeting some specific capability or some specific interface with the AI. And on one hand, this makes sense, right? Language is a very broad thing, and it can have a lot of nuance and very specific characteristics you might want to test. And to do that, you may need to build some specific data set that addresses it. So for instance, if I pop back here, this visual question answering data set is collected from people on the internet, whereas this one down here is collected from visually impaired or blind users. And it ends up the types of questions that are asked are different. So there seems like there's this problem that I have this very general capability of being able to take words or sentences and recognize them in imagery, but I have all of these little fragmented tasks that evaluates that capability. And if you look at each one of these tasks as an academic and you roll through these papers, what you find is that every task has a slightly different API, and the model that does best in that task right now, right? If you're an engineer saying, I want to go get the state-of-the-art captioning model, that model looks different than the state-of-the-art question answering model. There's this divergence across tasks. And this is disappointing that there's not more sharing going on here, because they, like I said, have this common need for visual grounding. And you say, okay, well, maybe that's all right. They're different tasks. But if you dig in and say, okay, well, what if I just care about question answering, right? I want my users to be able to upload an image and ask questions about it. Even in here, you see a different model being dominant in one data set versus another data set versus another data set. And these models learn data set specific groundings, right, that can actually be quite biased. The things you learn to answer questions from this data set won't be very useful to answer questions in this data set because they talk about different things. And that's somehow disappointing, right? If I want to eventually get to a place where I have a general enough AI to answer questions about whatever image my user puts out, this doesn't seem like it's on the right road path. So in this talk, I'm going to look at two questions following two pieces of work that we did in the last couple of years. The first is, how can we learn some generic visual grounding mechanism that transfers to many tasks? And this is going to be a lesson about going from something that looks like this, where for every type of task I have a different model, to something that looks a bit more like this, where they all share some common backbone, some common pre-trained and transferred model, and then some very small task-specific set of parameters. So if you've been paying attention to image classification, a lot of stuff in computer vision, this has been the trend for quite a while, right? Everyone starts with a ImageNet pre-trained ResNet or something, and then fine-tunes on whatever data they want. So we're asking if we can do the same thing to pre-train for visual grounding, for associating sentences or words with parts of images. So that's question one. And then question two, if we can do that, can we actually have one model do all of these tasks at the same time? And what does that gain us, right? This multitask learning, does it help or hurt our ability to do these broad-ranging tasks? So again, this story is about vision and language research, but it's also a story about transfer learning and multitask learning. All right, to get us started, I'll sort of go to section one of the talk, which is just learning these task-agnostic visiolinguistic features. So I want to learn some encoder that can represent images and text jointly. And then after that, I'll move on to this multitask problem. And this first section is going to largely be based on this Vilbert paper from 2019 with some collaborators at Facebook AI Research. Okay, so like I said a bit ago, one of the big trends in machine learning over the last several years is the rise of large pre-trained networks being transferred to other topics, right? So like if you've been working in vision, you will probably start any project by taking a ResNet that's been trained on ImageNet and then fine-tuning it for some downstream application, right? Object detectors are based on it, semantic segmentation algorithms are based on it, even structured outputs like pose estimation models are often based on it. And if you've been in the language community, it's been a story that parallels that one, right? So I'm going to take some very large corpus of text from Wikipedia or from a bunch of books or just scraped from the web broadly, and I'll train some large transformer model. So these are your BERTs or your GPT-3s or T5s or any of these gigantic language models or language encoding models that have really come to dominate the area in this last several years. And then I'll fine tune on some downstream tasks, right? So I'll take BERT and I'll use that as the basis for my question answering agent or the basis for my sentiment analysis agent, right? Nothing is trained from scratch because the power of this transfer is really quite strong. So assuming that vision gives us really nice representations of things, in this case, I'm saying that a pre-trained visual model maybe understands dogs really well, and my pre-trained language model understands the words golden retriever and dachshund and German shepherd really well. What's missing for a visual grounding perspective is the association between the words and the visual features. So when I talk about pre-training for visual grounding, what I really want to find is some connecting piece that can take large language corpuses, large visual corpuses, and produce a model that I can then fine tune to transfer to any one of those, many tasks that I talked about in this vision and language space. And that's sort of the hole that I tried to fill with this work, and other people have taken it and done some really amazing things at really high scales since then. But the model that we proposed at the time was something we called VilBERT, or Vision and Language BERT. And in a nutshell, again, it's a model that I want to pre-train and transfer, and it's composed of basically two parts. It is a large self-supervised multimodal transformer model. So this is sort of an architectural component about what the model actually is. And then it's trained on some large scale, Webley aligned image text pairs. So these are image text pairs that the text should describe some part of the image such that we can learn from it, but they're not really finely done human annotations. So to get through this, I'm going to break it down one part at a time and first talk about this self-supervised multimodal transformer. So for people who haven't maybe seen this before, our discussion can start by talking about this work from a few years ago, the bidirectional encoder representations from transformers, or BERT paper. And if you've studied anything in NLP in the last several years, this is a model that you've seen a bunch. But in essence, what it does is takes in a sentence A and a sentence B, and then for every word or token in each of these sentences produces some contextualized representation, some vector that describes this word or this token in the context of all the other tokens in these sentences. And under the hood, this thing is a very large transformer model where a transformer block is a sort of attention-based neural network. So it's a neural network that can do selection operations and attend to different parts of its input. And the actual nuts and bolts of what's going on in here is maybe less important to our discussion, but the idea that it takes in some input and produces a contextual encoding as the output. So for each word, it's going to produce an encoding. And these things are taken and applied to very large language corpuses or very large sets of text from the web typically. And they're trained using two objectives, and they're fairly clever things. The first is that they're going to randomly drop out words from these sentences and have to repredict them. So, Mary walked her blank around the park. You may replace that word with dog, given the context. And if you do that really well, that just says something about having learned the statistics of the language in a reasonable way. And this is what's referred to as masked language modeling. And alternatively, you could imagine taking two sentences, either sentences that are from the same text and follow each other, or sentences that are in reversed order or from different texts, and just answering the question whether the sentences relate to each other or not, right? So this gives you a higher level sentence sort of notion about whether the content is the same. And this was wildly, wildly successful, as I said before. You train this on a large data set, and then you use it as the basis for any downstream task. And the community noticed improvements across the board compared to fine-tuning, or compared to training from scratch. So what we want to do is try to mix language and imagery into sort of the same encoder so that we can get representations of our image that are contextualized with the text associated with them, or we can get text that's contextualized by the image features. And this is going to be able to give us these visiolinguistic features, as I described earlier. So the first thing you might do if you wanted to try to sort of push images into such a model is to take an image and break it apart into little pieces, little tokens, or in this case, little bounding boxes, encode them with some sort of pre-trained model, some visual model, and use those encoded tokens as the image representation. So now we have a model that takes in an image represented by parts of the image, and then some sentence represented by words. And would like, again, to have some representations on the other end that tell us a lot about both. And this is what we'd call a single stream Hilbert model. It's a model that does, as I said, takes in image parts, takes in sentence parts, and applies some set of transformers to get a final encoding. And we haven't talked about how to train this yet. That's sort of the next step. But just looking at this, it seems like there might be some challenges in this methodology, or at least it seemed like to us there might be some challenges. Sort of first, these different modalities may require very different levels of abstraction, right? An image region is perhaps much more complicated than something like the word man to represent, right? This is a continuous grid of pixels. This is a discrete token. So putting them into this network at the sort of same level of abstraction may lead to really difficult learning problems. And then secondly, it's sort of forcing these visual tokens into the same space as linguistic ones. So if we want to leverage the pre-training that we said is so great, we want to start with some pre-trained visual model and would like to start with some pre-trained linguistic model. And directly shoving these visual tokens into that linguistic space, we worried might damage training. So we ended up splitting it into sort of two streams, one that processes the vision for a little while, one that processes the language for a little while, and then the two branches talk in these very sparse co-attentional layers. So at the high level, you can think about the model as having a branch for vision, a branch for language, and these really rare communications across the two to intermix. And the nice thing about this is we can vary the number of layers for modalities. So if we think language needs more processing and more contextualization, we can do that. If we think vision needs more processing, we can do that. And we can initialize early parts with these pre-trained models, right? I can start my language side with this BERT thing. I can start my visual side with some sort of encoder from a ResNet. And to train this thing, to actually make sort of sensible representations that represent both language and text, we can borrow and modify those same objectives that I described in BERT. So I could imagine taking an image and a description of that image and masking out parts of it, right? So I could mask out one of my words and have my model have to repredict it. So how will the model know that it's a man shopping? Well, it'll have to look at the visual evidence in order to produce that. And likewise, if I mask out part of the image, it'll have to use the text and the rest of the image to be able to understand what's in that region and correctly predict out that same visual feature or something similar. So this lets us do sort of low-level part of image alignment with words and learn nice representations. We can also do sort of high-level things where I encode an entire image and I encode the full description. In this case, there's no masking. And I can just ask the simple question of, does this image relate to this caption? Right? Is this sentence descriptive of the content of the image or not? And this will give us a higher level alignment supervision. So that's Vilbert. It's this large multimodal transformer model. It takes in images, it takes in text, and it produces these contextualized representations on the other end. And again, these tasks themselves may not be inherently useful, but we're looking for objectives that allow us to do self-supervised pre-training and then transfer to downstream tasks. So that's this first part. That's the structure of the model. And the second part is, what data are we actually going to use to train it? And what we need is image text pairs, right? I need an image and some sort of text that describes it, but I need to be able to get it cheaply, right? I need to be able to find it in large quantities so I can learn very broad skills without having to, have massive piles of annotation. And back in 2018, a group out of Google produced a data set known as conceptual captions, where they played this really clever trick. They went out to the web and found any image on the web that had an alt text. So if anyone has ever done sort of web development or just hovered over an image for too long on a web page, you can specify a written description of an image that loads when you mouse over it, or loads on certain accessibility software, or if the image just failed to load for some reason, that describes its content. For instance, there's this fellow here, and the alt text is, a musician, Justin Timberlake, performs at this festival on this date in this city. And this is fine, but there's not much visual evidence for any of this, right? So if I wanted to train a model just on this sort of image and this sort of text, there's this problem that I don't really have good visual evidence for the fact that this is Justin Timberlake. I don't have good visual evidence that it's at this pilgrimage music and cultural festival. I definitely don't know the date based on the image, and I certainly don't know the location. So as far as training supervision goes, this maybe has too many details that aren't visually grounded. So these clever folks at Google did this thing where they sort of limitized and sanitized these alt texts to something that's more generic. For instance, a pop artist performs at the festival in a city. So it replaced all these proper nouns with more general nouns. And I can show another example here. A Pakistani worker helps to clear the debris from the Taj Mahal Hotel in Balakot, Pakistan. And it got transferred to a worker helps to clear the debris. Or this description of a sculptor gets transferred to sculptors by person adorn trees outside the derelict offices. And you may notice that these aren't perfect, right? At the festival in a city is a bit unclear, right? This festival could have been like Woodstock out in a field somewhere. It's not necessary that it's at a city. It may not be a festival versus just a single concert. It's not clear that these offices right here in the background are actually derelict. There's these parts of these captions that are still not perfectly visually grounded. So these are noisy associations between the imagery and the text that describes that imagery. However, there's about 3.3 million of these pairs. So the strategy here is, even though it's noisy, we have enough of the data that we think we can still learn reasonable associations just based on scale. And this is a trend that will be repeated many times in work that followed. So if people are familiar with things like CLIP, they didn't even do this caption deriving. They went straight for alt text. Okay, so we'll take our model architecture that I described, we'll train it with these two losses, the one that is trying to predict whether the text matches an image, and the one that masks out tokens and then tries to repeat them. And we'll train it for some amount of time, initializing with these pre-trained models. And after going through all this work and listening to me for this long, there's this question about like, what does this model actually learn from pre-training? What capabilities have we captured? And I want to talk about a couple of different ways to assess that before I go and look at extrinsic evaluation on downstream tasks. So this is just going to be looking at the trained model itself and what it's captured. So the first thing we could try to do is to sample captions from this, right? So for instance, if I give it an image, I could mask out all the tokens on the right and sample out a caption. A and then put A down here, man, and then put man down here, shops, put shops down here, and keep repeating. And I can give some descriptions or some examples of what our model produced. So after we finished training, we gave the model this image of this young woman, and the caption was a happy, young, successful businesswoman in all black suit, smiling at a camera in the busy office. And, compared to ImageNet saying that this is a person, I'm actually pretty pleased by the descriptiveness of this, right? She's smiling, so visually she looks happy. I don't know her age, but she's dressed in a black suit and presumably a businesswoman. That's a fair guess. And I don't know if the office is busy or not, but in general, it describes the content remarkably well. And similarly, I gave it this random picture of a map, and it replied, a gray textured map with national flag and binary code isolated on a white background. And some of that is fluff and it's not right. But the fact that it recognizes it as a map is actually quite interesting, because as I said before, a lot of the prior work in this space is trained in these really narrow domains, so that a model that could recognize this woman certainly couldn't recognize this map in the way things used to be done. As our last example here, there's this apartment building face, and our caption was new apartment buildings on the waterfront in a residential development built for cleaner housing. And these aren't perfect, but they're recognizing interesting things about the images. And there's one more. This is a bunch of fireworks, and it's the concept comes to life with a massive display of fireworks that will fill the grounds. And some of you may have noticed that there's these parts in these sentences or these generated captions that don't really align to anything in the image, and it has this bit of editorializing feel to it. Part of that is from the data, right? It ends up that on the web, places that really like to put in alt text tend to be news sites because they want to make sure they have accessibility. So some of this is directly editorializing from the alt text. But in general, it recognizes concepts reasonably well. If I want to use this as a feature encoder, this is a good sign. So how else could we look at what this model has learned? Well, I said there's these attention components in this model, and I could do what is often done in the literature and try to look at the distribution of this attention across images and text. But anytime I look at this, my eyes sort of go cross and I don't know how to think about it because there's just too many of them. But I can look at something we derived from these attention maps. So in this example, what I'm looking at is image to sentence attention. So I'm going to look at boxes in the image and ask, for this box, what word in the sentence did it associate most strongly with the contents of the box? And I can do this multiple times across different sort of points or different levels in this network, and we can have a look. So for instance, these boxes here are really strongly associated with the word white from the sentence. And this is at a very specific point in the network. If I go to a different point in the network, these boxes here, the cyan ones, are associated strongly with the word sheep. And again, they surround the sheep. So if we wanted to decide to try to see if our model understood what a white sheep was, it's certainly co-located white and sheep here. And we also have these red boxes surrounding the child, and we get boy as the largest attention. And this one's actually hard to see, but if you follow my little pointer there, there's this dark green box that's circling the nose of the sheep and the hand of the child. So just this area right here. And that's strongly associated with the verb pet. So this interaction point has been strongly associated with this verb. And, we can keep doing it. We can find, the boy again at a different layer. We can find the white sheep and the boy again. And we can even find the mom here. We have this blue box surrounding this mother. And I want to emphasize that this thing is not necessarily trained with any sort of association between the words and regions of the image, right? It's given image regions, it's given words, and the association it's learning is due to the statistical regularity in the data set. That the regions that look like sheep tend to be associated with the word sheep. Images without sheep don't tend to have that word. So this sort of grounding to specific regions of the image is something that's an emergent property. It's learned it as it went along. Okay, so I've said that my goal here is to pre-train this thing and then transfer it to some downstream tasks. And the tasks we transferred to were some of the ones I originally showed, like visual question answering. So given an image and a question, give me the answer. We also have another question answering data set that looks more at people's intentions from scenes in movies. We have this referring expression task where I get an image and a description of some part of the image, and you're supposed to localize it. So you can think of this as like language-based object detection. So if I want to find the guy in yellow dribbling a ball, I need to circle this guy. And I looked at caption-based image retrieval. So if I give a sentence and I have this large image collection, give me the image that most matches the sentence. So you can think of this as a really advanced version of like Google image search that cares about language quite a lot. So these are our 4 downstream tasks that we looked at. And for each of them, I can do them with very small modifications of my base architecture. So I'll train Vilbert and then train only these really tiny red portions, which are fully connected layers or something like this on top of it. So really small additions in the number of parameters. And we've gotten to the sort of most boring part of a talk where I'm going to quickly show some bars. I want to show where Vilbert is on each of these tasks. And I don't have a labeled axis, but higher is better for all of these. And I want to compare to sort of a single stream model. So a model that we talked about at the beginning that doesn't have a separate vision and language branch. And we see that in general, that does worse than our dual stream model. And if I look at the difference between our Vilbert model and our Vilbert model without the pre-training, this really speaks to that power of transfer learning, right? So if you compare the green bars, the hatched green bar is a model that didn't go through all of our conceptual captions pre-training, and the solid bar is the one that did go through that pre-training. And across the board, you see improvements. And in fact, as the data sets get smaller, like these 3 over here are much smaller than the first one, the improvement you see is increasingly stark. And that's the common trend for transfer learning. So if there's a moral to this part of the story, is we found a lot of data, we pre-trained a model on that noisy data, but then we were able to use those representations to perform well at downstream tasks. And at the time, we were state-of-the-art across all 4 of these tasks, but progress has been made since then. Okay, so this first part is basically wrapping up, and the takeaway is that we went from sort of we made a single pre-trained baseline architecture that was transferable to all these tasks. So we went from the thing on the left with a bunch of bespoke models for each one to a single model doing all sorts of stuff. And there's a bunch of later works that have repeated this sort of observation with different models and a bunch of different tweaks, and they vary along a couple of different axes. So that wraps up this first part of the talk where I'm going to talk about this task-agnostic option, and then I'm going to move on to multitask learning next. Alan, I know I've been sort of talking without breath, so is there anything in the chat?
No, you can continue.
Thank you. All right, so we're moving on to sort of the second chapter of this, where we're going to go from pre-training a model and transferring it to having a model do all of these things at the same time. And this follows from this 2020 work from a few years ago. So what we did before was we pre-trained this Vilbert model, and we had this backbone that we could transfer to other tasks. And what we did is then transfer it to this other task that had really nice human supervised grounding. So a lot of these downstream data sets were really clean data sets, at least compared to conceptual captions. So for instance, we might get an image and the phrase swimming elephant, and in a referring expression task, it would have to find the elephant. Or I might get an image and a question about what's going on in the image, and I might have to say that, that baby elephant is actually swimming. And you could imagine trying to do these two tasks together, right? I might say, okay, given the image and the question, I'll predict swimming. And given the image and this referring expression, I'll find the swimming elephant. And you might hope that by doing these together with the same base model, that you would learn more about elephants and you would learn more about swimming. So to do this, I need some sort of model that I can do multitask training with. I need some set of tasks and data, and I need a way to train. And the model is exactly this Vilbert thing that we just talked about, plus or minus a couple of tweaks to make it train better. So nothing new to learn there. On the dataset side, we actually looked at 12 different vision and language datasets, and they fall into a couple of categories. We looked at 3 question answering datasets that, as I said before, is given an image and a question, produce an answer from some finite set. We looked at caption-based image retrieval. So given a set of images and a sentence, give me the most related image. We looked at multimodal verification datasets, and these are logical expressions regarding images. So for instance, given an image and the statement, no elephants in this image are swimming, the model has to either predict that this is a correct entailment or if it's a contradiction of the image content. And then finally, we looked at a set of these referring expression datasets. These are sort of the language conditioned object detection datasets. We're given an image and an expression, I have to find the part of the image that matches that expression. So these are typically noun phrases. So these are the things we were looking at trying to do all at the same time and see if we can share representational power by doing multitask learning. One little bump that we had, and this is maybe a practitioner note, is you have to be really careful when doing multitask learning that the data sets are actually separate. So for instance, we found that in the training set for some task A, you might find something like this that has, given an elephant, describe its content. But in the test set for some other task, you may find that same image, but with a question instead. And it's believable that learning to do this task on the left might help you do this task on the right in an unfair and sort of overfitting kind of way. So we did have to go through and make sure that our data sets were completely separate. And we did end up losing about 13% of our data when doing this cleaning mechanism. So just when you're doing multitask learning, try to watch out for that so you don't overinflate your test results. We also need some way to train, right? So if I said, here's 12 different data sets with different APIs, how would you actually go about training that? And we went with a fairly simple strategy of what is essentially batch-wise round robin. So you take one data set, take a batch from it, train your model one step. Move on to the next data set, take a batch, train your model one step. All the way around on all 12 of the data sets and then back to sort of the beginning. And one challenge with this is that data sets differ in size and sort of the number of epochs needed to train or the difficulty of mastering that data set. So if we just did this without thinking, we would overfit on some data sets terribly while underfitting on some data sets quite a lot. So to do that, to try to address this, we sort of made a natural extension to early stopping, which we called dynamic stop and go training, which we probably should have named different. That went something like this. Every epoch, we would check the validation loss on a task. And if it has saturated, right, if it hasn't improved by a certain percentage over a certain amount of time, we would reduce the rate that we sampled from that task. So it would, every 5th iteration, we'd take a batch from it instead of every iteration. That parallels with normal early stopping, right? Whenever I make my agent stop because validation loss is going up. The tricky thing here is if I stop training on one data set, I'm still training on the other ones. And as the sort of baseline or the trunk of the model adapts to those other data sets, I can get worse at a model that I previously stopped. So we also monitor validation loss. And if it has gotten worse over time, we turn that back on. So you can think of this as sort of turning off or on, or changing the speed at which you're training on these different data sets. And essentially, if we're in this go mode, we get batch every iteration. Otherwise, we get a batch every D iterations. And this actually gave this really fun experiment we can do where we'd run all of these data sets together, and I can talk about when they're in this fast mode or when they're in this slow mode. So like when they've converged and when they still need more training. So on the plot on the right, I'm going to show what happens as I go through training about the whether a individual data set is in this fast training mode or this slow training mode. So for instance, when I start out, all the data sets are more or less in that full training mode, but these three, which are quite small and somewhat easy, are already starting to stutter out and stall, right? Their validation accuracy is not improving anymore. If I step out to 10,000 iterations instead, you see more of this sort of sputtering behavior among some data sets, while other data sets are still making progress on their loss. Step out even further, some of them have started to actually finally converge and not stutter, while others are still going. And if I keep going out, you see this trend of some data sets converging really quickly and being stable, some needing to come back on and off over and over again, and some taking almost the full time to completely converge. And one of the scientific questions we had upon seeing this is, what is this? Is this a function of dataset size or difficulty or something like this? Why are some of these taking longer to converge than others? So we plotted the number of updates seen during training versus the dataset size for each of these. And you'll notice that there's these groups that are all pretty similar on the x-axis, right? They all have about the same amount of data, but the amount of updates they require are quite different. So it sort of goes to show that when doing multitask learning, you may have harder or easier tasks, and they may converge at very different rates, even with the same amount of data. And we see the same thing here in this next group of things, data sets. So there is a general trend that more data takes longer, but within a comparable data stack, there's a good amount of variance. So once you have this whole setup where you can train different tasks together, you can ask questions about how various tasks affect other tasks. And I think sort of for the sake of time, I'll breeze through this part for now. But you can imagine turning on or off different tasks here to try to identify which groups affect each other. So I'm going to skip this bit here. It's a little technical. And look at this bit. So the first thing you might do and ask here is like, okay, if I have 3 tasks that are really closely related, does training just those 3 together lead to significant improvements, right? Do I need diverse tasks in order to get improvements, or do I just need more data of similar tasks? And what I'm going to show here again is sort of this group average gain, which will be an improvement over just training a single model. So if I train this model just on the associated tasks, so for instance, this vocab-based VQA model is a model trained on 3 visual question answering data sets. This is a caption-based model trained on 2 caption models, etc. If I compare the group version versus the all version, right? So the small hatch versus the large hatch, the tight hatch, what I see is that for some tasks, training on diverse tasks, so training on everything, leads to improvements. So when this tight hatch is higher than this sparse hatch, it means that we gained something from training a model across all the tasks versus just the tasks within the category. So for referring expressions and visual question answering, this helped, but for caption-based image retrieval and multimodal verification, for caption-based image retrieval, this hurt substantially, right? We lost almost all of our gain when we did this. And digging in this, we actually found sort of an adversarial relationship between these 2 tasks. So when you're doing multitask training, it could be that 2 of your tasks sort of have gradients that are oriented opposite each other, that doing well on one task will tend to hurt you on another. So if you're trying to boost performance with multitask learning, doing this sort of finer grained task by task analysis can help you push things further. And then in terms of absolute performance for these models, we had something that looked very similar to the previous story, right? So Each of these bars is one of our Vilbeck models from last time, trained just on that specific data set. So for instance, here, this is a bar just trained on this data set, whereas this is a model's performance just trained on this data set. And of course, these all have very different metrics, so I'm not labeling the y-axis, but the relative changes within groups is what we're looking for. So this is no multitask training at all. In contrast, if we do multitask training, so if we're doing a training on all 12 tasks at the same time, in general, we're seeing improvements, right? For 10 out of 12 of these problems, our multitask model did better than an independent model trained just on that data set. And of course, remember that I had to clean these data sets a bit, so this is actually even with less data in the specific tasks. Of course, you may be a person who says this is great, but I'm really interested in doing one task really well, right? Can multitask learning help me if I only care about a single task? And yes, you can get a small improvement here is sort of one of the answers, but you could also then take this multitask model and do transfer learning and sort of fine tune it on just one of these tasks. So if you do this multimodal pre-training, if you then do this multitask training and then fine tune it on just your one task, making it task specific again, what happens? And we see further gains. So not only does multitask learning help improve your model's performance, the representation it gives you is a better starting point if you're going to do downstream fine-tuning on your task. So multitask learning seems to be this additional pre-training step you could imagine doing to eke out a little bit more performance. And at the time, we set sort of state-of-the-art on 7 out of 12 of these tasks. So I want to dive into some qualitative examples of what our model is doing here. So again, this is all one model doing all of these tasks, and these are real model outputs. So given this set of 4 images, giraffe, zebra, zebra, giraffe, if I'm given the sentence, 3 zebras are grazing in a grass field, it picked out the image in which 1, 2, 3 zebras are grazing in a grass field. It didn't pick the giraffes, and it didn't predict the zebra that are fighting over there. Likewise, if I have these sort of elephants and bears, and I give it the question, elephants are bathing in the river water, it pulls out this image of the elephants in the water rather than the other elephants. If I take this bottom image and I say, find me a swimming elephant, it correctly circles the swimming elephant. If I ask, which is the baby elephant, it puts a circle around this younger one. If I say, find me a baby zebra, it picks the smaller zebra standing here in front of the adult. If I look for trees, it circles trees. If I have this dialogue, which entity is it? Zebra. Is it on the left? No. Is it eating grass? Yes. And then it points to this rightmost zebra eating grass. If I say, is the baby zebra standing next to the zebra on the right? It says yes. This is sort of more of a spatial reasoning question. If I ask how many zebra there are on the right, it says 2, just these 2 on the right. If I ask where are the elephants, they say in the water. If I say no elephants in the image are swimming, it tells me I'm a liar. And if I say none of the animals in either image is swimming, it tells me I'm a liar. So these are all those 12 different tasks. These are samples from that sort of those data sets on these images. And the idea is that one model is handling all of this linguistic and task variation, right? The way I'm interfacing those models is very different, but the results it's producing are still really good. All right, so just to wrap up what we talked about today, we said that the way people were dealing with these visual grounding tasks, these vision and language tasks, were to develop a special model for every sort of data set. And that makes it hard to track progress, and it's also not in line with the power we've seen from pre-training and transfer learning. So in this talk, I described 2 works. The first that built a model for pre-training visual grounding, and then another that did multitask training to bring all these tasks into a single model at the same time. And we saw improvements whether you care about individual tasks or if you care about the tasks at large. So I'll stop there and take questions.
All right. Well, thanks a lot. That was really interesting. Yeah, as I watch this, I'm always thinking back, if you had shown me this 5-6 years ago, be like, no way. It's really amazing how fast things are moving these days. So we've got a couple of questions in the chat. So yeah, this was a question I had actually by Abhinav. So how are captioning and multimodal verification adversarial during the training? Like that wasn't intuitive to me.
Yeah, so there's not an obvious answer there, and we've dug into a little bit, but nothing very satisfying. But here's sort of the example tasks. So these two task box here are these multimodal verification tasks. And they're given an image and a caption and trying to decide at a really fine grain whether or not that caption is perfectly descriptive of the image, right? So it's not enough that it's plausible, it has to be, perfectly entailed, or it's neutral, right? So you can't hallucinate anything in these, right? So if I said, 2 elephants in the image are swimming, that would be a contradiction as well. It's very, very fine grained. On the caption-based retrieval side, it's fuzzier, right? 3 zebras in a grazing in a grass field. This is a pretty good example, but like if it pulled back a different zebra, that maybe wouldn't be the worst thing in the world. Right? There's a big wide variety of what it could pull back. And for some reason, that difference in API caused a lot of trouble where sort of these 2 tasks got a lot better while hurting these tasks. So it was almost sort of a parasitic relationship. And if we got rid of those 2 tasks in some of the analysis we did, image captioning or image retrieval went up, just like with the other multitask tasks. So something about that interaction just did not like the optimization, and we haven't really figured out why in this big mess of parameters.
Yeah, interesting. Then, so yeah, Sandia, she's got a question here. I'll just read it. So there's been effort in the past to identify optimal stopping points for algorithms and improving solution quality using a portfolio of algorithms. So there's, a long history on portfolio approaches to solving problems. So she's wondering if those analogies and insights can be used to automatically sample and train with multimodal data sets, as in tuning the weights for different data sets.
Yeah, I mean, the answer is sort of probably, right? There's a lot of great work that exists in the past, right? What's the rule? If your paper doesn't cite something from more than 10 years ago, it's probably missing something. But in this case, we did something fairly simple and it worked. Since then, some multitask literature has really focused in on sort of the gradients of the different tasks and whether or not they align. So you could imagine looking at pairs of gradients from your various tasks and projecting them so that they're non-destructive, right? So taking a step for task A results in a gradient that is at least sort of got a cosine similarity greater than 0 with the gradient for some other tasks that you have estimated. And these sort of non-destructive gradient intervention things have worked fairly well to avoid some of the problems that we maybe saw here, which doesn't tell us about the right training strategy, but it does sort of let these tasks maybe train together without as much trouble.
Yeah, if only we could get these things to stop forgetting what they've learned.
Yeah, I mean, we had to turn those things back on a lot before it figured it out, right? Off and on over again.
Yeah. So since we're close to the end of the time, I wanted to ask a question myself. So yeah, as I said, like if I think back 5 years, like this would have been almost unimaginable, even just 5 years ago. So if you think ahead 5 years, what do you think is going to surprise us in this sort of domain, visual, language, interaction?
Yeah, I mean, I can tell you what's surprising me today, and whether that keeps being surprising in 5 years may be different. But the combination of language and image generation has started to become eerily good. Not amazing, but like increasingly reasonable, where you may come to the day where you Google search something and instead of giving you a real image, it just makes you one, right? You Google search 3 ducks riding on a camel and it just produces that for you. Never before in the history of mankind we have one, it just gives it to you. And what that'll do to creative work is a really interesting question on the societal level, right? If art is describable and generatable, that'll be very interesting in a number of industries. And then on the actual technical side, the thing I'm most interested in is how do we do fast binding here, right? So like this is impressive, but it's also like saying I'm impressed that a college graduate can spell, right? We've trained it for a bunch of things. It's seen all this stuff. But in a human, I can point to a new object and say, this is my blip. And we can start talking about my blip or categories of my blip, and I can refer to it, and that's fine. And this is analogous to something like one-shot or few-shot learning in the traditional machine learning sense, but you could imagine it with compound adjectives, right? So I could say like, this blip is zippy, and you don't know what zippy means, but if you observe me long enough when we talk, can you learn really quickly what that adjective zippy is and what it might apply to other stuff? So I think that sort of extension beyond training set to new concepts will be one of the big challenges. And if we can get over that hump, it'd be really impressive linguistic models.
Yeah. Do we have any, just a quick thought, do we have anything right now that's close to being able to, so now just give it, a blip example that an infant would easily digest and not forget anything because it just put a blip in its head. Do we have anything like that yet that's close?
So there's some work out of Felix Hill's group at DeepMind that did some sort of similar training procedure here, but with a frozen GPT-3 model, basically. Mm-hmm. So they learned an image encoder such that images look like words to GPT-3, and GPT-3 then would produce the rest of the sort of caption from that. And they had a couple of examples of sort of in-context learning, right? Where I give an image and say, this is a blip, and then I can talk about the blip and it can answer appropriately. But that was largely on, A, it's small and qualitative, and B, it was largely on known objects, right? In infant language developmental studies, they show entirely new objects and give them names. So there's this difference between anchoring a known object to a new name, right? Synonym learning versus anchoring a new object to a new name, which I haven't seen yet.
Well, maybe in a year or two, we'll be seeing that. We'll see. And who knows, 5 years ahead. Yeah, you're probably right. It's really hard to predict.
Yeah, 5 years is beyond the horizon.
Yeah. All right. Well, thanks a lot. That was really interesting. And everybody will be back in 2 weeks.